So we are going to continue our discussion in chapter 6.2 talking about the binomial distribution, and this is one way that we will look at probabilities. So our objective is to determine whether a random variable is binomial. We're going to determine the probability distribution of a binomial random variable. We're going to compute binomial probabilities, and we're going to compute the mean and variance of a binomial random variable. Objective 1. Determine whether a random variable is binomial. Suppose that your favorite fast food chain is giving away a coupon with every purchase of a meal. 20% of the coupons entitle you to a free hamburger, and the rest of them say better luck next time. 10 of you order at lunch at this restaurant. What is the probability that 3 of you win a free hamburger? In general, if we let X be the number of people out of 10 that win a free hamburger, what is the probability distribution of X? In this section, we will learn that X has a distribution called a binomial distribution, which is one of the most useful probability distributions. So in the problem just described, each time we examine a coupon, we call it a trial. So there are 10 trials. When a coupon is good for a free hamburger, we will call it a success. The random variable X represents the number of successes in 10 trials. In this case, the probability of success was 20%. The probability of a failure was 80%. So, a random variable that represents the number of successes in a series of trials has a probability distribution called a binomial distribution. The conditions are as follows. A fixed number of trials are conducted. We call this n trials. There are 2 possible outcomes for each trial. One is labeled success, the other is labeled failure. Typically, we represent the probability of success and the probability of failure. The probability of success is the same on each trial. In other words, the probability of success cannot change between trials. The trials are independent. This means that the outcome of one trial does not affect the outcome of another trial. And finally, the random variable X represents the number of successes that occur. So in our notation, we'll have n is the number of trials and p is the probability of success. So here are some examples. Decide if each of the following represents a binomial experiment. A fair coin is tossed 10 times. Let X be the number of times the coin lands on heads. This is a binomial experiment. Each toss of the coin is a trial. There are 2 possible outcomes, heads or tails. Since X represents the number of heads, heads counts as a success. The trials are independent because the outcome of one coin does not affect the outcome of the other. So in other words, the probability of success in this case, if it's a fair coin, is equal to 0.5 or 1/2. The probability of failure is also equal to 0.5 or 1/2. So in the next example, 5 basketball players each attempt a free throw. Let X be the number of free throws made. In this case, this is not a binomial experiment. The probability of success of making a shot differs from player to player. So the probability of success is not the same for each player. Therefore, it's not binomial. And that's because each player will not have the same skills at making a free throw. In the last example, 10 cards are in a box. 5 are red, 5 are green. 3 of the cards are drawn at random. Let X be the number of red cards drawn. Again, this is not a binomial experiment because the trials are not independent because this is sampling without replacement, and we know without replacement it is conditional. Had we returned the cards after we've drawn them each time, then it would be a binomial experiment. Determine the probability distribution of a random variable. So you will recall in algebra the exponent rules. So in this section we'll be using the idea of exponents to calculate probabilities. Recall from elementary algebra the expression 2 times 2 is equal to 4 can be represented as 2 raised to the power of 2. Now suppose we have 2 raised to the power of 5. On the calculator, we could just calculate it. 2 with the caret symbol, 5 is equal, and hit enter, and we would get 32. But in reality, we get this statement. 2 to the power of 5 is equal to 32. Also in this chapter, we have something called a factorial, so that a factorial is nothing more than multiplication of the numbers up to a number of the factorial. For example, 5 factorial is nothing more than 1 times 2 times 3 times 4 times 5, which is 120. Note, on the TI-83 or 84, you can use the math key and move the cursor over to the probability option and then select the factorial if you wanted to calculate a particular factorial. So, for a binomial probability distribution, we consider the experiment of tossing a coin 3 times, that is biased in this case, with a probability of success of 0.6 of coming up heads. So, in this example, X's success is the number of heads that come up. We want to compute the probability that X is equal to 2. That is, exactly 2 of the tosses are heads. It turns out there are 3 arrangements or 3 ways of 2 heads in 3 tosses. Here they are. And the probability of HHT is just 0.6 times 0.6 times 0.4, right? We just multiply the probabilities. So we can change that into an exponent form of 0.6 raised to the 2 power times 4. And indeed, we know that the other 2 probabilities of happening have the same probabilities. So now, because we have the success, the probability of X equals 2 heads, we have 3 ways of choosing that. So we multiply 3 times the probability of success of 2, so we use the exponent, and then there's only one failure in this case, which is 0.4. Right? Examining the results, we see there are 2 successes and 1 failure in heads. In general, this number will be the number of arrangements or the number of ways that X is in success in n trials. We represent the number of ways that we can choose X successes in n trials as n CX, which is called a combinatoric. The number 0.6 is the success or the probability of P, which has an exponent of 2, the number of successes of X. The number 0.4 is the failure of probability 1 minus P, which has an exponent of 1. So, in general, the formula for calculating X successes is the number of ways that I can calculate X out of n trials times the probability of success times the probability of failure. raised to their various exponents of successes and failures. So now our objective is to compute some binomial probabilities by hand, and we'll also see how the calculator does it as well. So, in our first example, the Pew Research Center reported in June of 2013 that approximately 30% of the U.S. adults own a tablet computer, such as an iPad, a Samsung Galaxy tablet, or a Kindle Fire. Suppose a simple random sample of 15 people is taken. Use the binomial probability distribution to find the following probabilities. Find the probability that exactly 4 of the sample people own a tablet computer. Find the probability that fewer than 3 people own a tablet computer. Find the probability that more than one person owns a tablet computer. So in this case, the probability of success is equal to 0.3, and the probability of failure is equal to 1 minus 0.3, right, which is equal to 0.7. So in solving the first case, we note that n is equal to 15 and p is equal to 0.3. Find the probability that exactly 4 of the sample people own a tablet computer. So with 4, exactly 4, we want to calculate the number of ways that I get 4 from 15. And the way that calculation works is I have 15 possibilities, and I divide out the 4 successes factorial. These are all factorials. And I subtract out 4 minus 15, and that gives us the number of ways of choosing 4 people out of 15. Okay? Now we calculate the probability of success, which is 0.3 raised to the 4th power, right? Because there were 4 successes. And then we know that the probability of failure was 0.7, and we're left with 11 of those individuals that don't have a tablet. So what's the probability of this event? It turns out to be 0.219. Now in our calculator, we can utilize something called second vars. So if we hit the second vars key on our calculator, we go down to the option Binomial PDF. And then in parentheses, we put in 15 for the number of trials, then the probability of success, then what x is, the number of successes, 4, and we hit enter, and we get the following number. Pretty easy to do it that way. So B says find the probability that fewer than 3 of the people own a tablet. The possible numbers of people that are fewer than 3 are 1, 2, and 3. So in this case, we have to calculate each of these probabilities separately. So we go through the process of calculating this probability here, which is the first probability for 0. Then we calculate this probability here for 1. And then we calculate this probability here for 2. And we add them all up. And in this particular case, the probability that x is less than or equal to 2 is equal to 0.126. 7, approximately. But we can also use our calculator, but now we have to choose a different option. Instead of binomial PDF, we choose binomial CDF, which allows us to compute all of these different probabilities that is less than or equal to 2. So in this case, when we select binomial CDF, we can put in for n, 15. We can choose 0.3 as our success, probability of success, and 2 is being 2 or less, fewer, in that expression. Then we hit return, and here is our calculation. So we get to use the complement feature of probability. It says find the probability that more than one person owns a tablet. Well, we use the complement rule because of more than one is just 1 minus 1 or fewer. So in this case, what we can do is calculate the probability of 0, 1 first, because that's going to be easier to do than calculating the rest of the 13 probabilities going from 2 up to 15. So when we do that, we calculate the 0, 1, the probability that x is equal to 0, plus the probability that x is equal to 1. We add those together, we get this number here, but then we have to use the complement, right? Because the complement, what we're really trying to find is the probability of more than 1. So we subtract 1 minus 0.035 and we get 0.96. On our calculator, we can do the same thing, and we can calculate the first part, the probability of 1 or 0 first, which again is 0.3526, whatever, and then we can subtract 1 from it to get the final result. Again, very easy way to do it on the calculator. So now we just want to review some of the ways to calculate binomial probabilities on the TI-83 and 84. There are two primary commands. One is called the binomial PDF, and the other one is binomial CDF, right? And these commands are on the distribution key menu, accessed by pressing second vars. The binomial PDF command is used when finding a probability that is the binomial random variable x is equal to a specific value x. The binomial CDF is a command used when finding the probability that a random variable x is less than or equal to a specified value of x. And so when you get to second vars, you keep moving the arrow key down until you find either one of these two options. So the idea here is that to compute a probability for the probability that, say, x equals 2, 2 would go here, n is the number of trials, and p is success, right? In the binomial CDF situation, the probability that x is less than or equal to 2, 2 would go here in this case, and then we have the number of trials and the probability of success. You will notice that these two probabilities are different. One is equal and one has a less than or equal than sign. Objective 4 is to compute the mean and variance of a binomial random variable. So the mean variance and standard deviation of a binomial random variable with n trials and success probability of p is relatively easy. The mean value is just the number of trials times the probability of success. Very simple. The variance is just n times p times the probability of failure, and that is the variance. And if we take the square root of that, we get the standard deviation. So here's a calculation for a particular problem using the binomial. The probability of a new car of a certain model will require repairs during the warranty period is 0.15 or 15%. A particular dealership sells 25 such cars. Let X be the number that will require repairs during the warranty period. Find the mean and standard deviation of X. Well, there are N equals 25 trials with P is equal to 15%. So the mean number of cars we would expect to see that will require repairs during the warranty period is 3.75. And the standard deviation is 1.785. So in this chapter, you should know the following: how to determine whether a random variable is binomial, the notation for a binomial experiment, how to determine the probability distribution of a binomial random variable, how to compute binomial probabilities, and how to compute the mean and variance of a binomial random variable. Well, that concludes Chapter 6 that we're going to cover. We will not hit all of the high points in class, so please review the videos. Thank you.